In this section, we're going to look at more complicated functions. So we'll be using the same basic 5 formulas that you've already learned, except this time we're going to have to do some substitution in order to get more complicated composite functions into the form of our original rules. So first, let's go back to differential calculus, and let's look at this function. F of x is equal to 3e to the x cubed. If I take the derivative of that, f prime of x, the 3 is a constant multiplier. The rule for derivatives of e to the u are to repeat the function, e to the u, and then multiply by derivative of the exponent. Derivative of x cubed is 3x squared. So when you think back about what you did with the chain rule, we have a function here. We called that the inside function. And then when we took the derivative, this piece is the derivative of the inside that we multiplied over here. And this first piece here is the derivative of the outside. That was the chain rule. So what we're looking at now is, suppose I start off with something this messy, and I want to go back and find the original function. Using the letters that we did before, this would actually be our capital F, because this is the original. This would be the antiderivative of our little f, which is the same as the derivative of capital F. Okay. Let's look at another function that involves the chain rule. Okay, f of x equals 4x cubed plus 7 to the 8th power. To take the derivative of this, we have to use power rule. So f prime of x is equal to the outside power comes around front. You subtract 1. The inside function does not change. But because of the chain rule, we now have to multiply by the derivative of the inside. 3 fours are 12. Subtract 1 gives me x squared. So that, again, I have a function where I have the derivative of the outside, the 8 times that to the 7th, multiplied times derivative of the inside. So when we think about solving to get the antiderivative of this, we have to be very sure we have all the pieces to this problem. So let's go back to that first problem. We're going to start off with some function f of x equal to 9x squared e to the x cubed. Make that look more like an x. 9x squared e to the x cubed. This is my function, and I want to find the antiderivative, the integral of 9x squared e to the x cubed. And since there's an integral sign, there needs to be a dx. So how do we go about doing that? Well, we have steps. Our first step, number 1, we're going to do something called choose u. Remember when we talked about rules for derivatives, e to the u, and then we multiply by the derivative of the exponent, the derivative of u? That's what we want to do first, is figure out what is the inside function. Well, we already decided that x to the 3rd was the inside function. So let's let u equal x to the 3rd. Now, the second thing we want to do, we want to find something just called du. We have dx right here. That told us that in this integral, x is the variable. To find du, well, one thing I know I can do, I can take the derivative. I can find u prime. I just take the derivative of that. So u prime can also be written as the derivative of u with respect to x. And when I take the derivative here, I get 3x squared. But I want a du if my variable is u, like I have a dx when the variable is x. So to find du, I multiply the right-hand side by dx. My third step. What I want to do now is rearrange this integral so I can have it in a nice, neat form. Now, think about what kind of integral rule we're going to use here. We have e raised to a power. One of our integral rules is the integral of e to the u du, which is another way to let me know what to choose for u if I have e to the u. Let me rearrange this. So I have e to the x cubed first, and then I have all this other stuff, but my du is 3x squared dx, and I have 9x squared dx. I'm going to write that 9 as 3 times 3x squared, and then dx. So I'm splitting this up. I'm rewriting my integral in terms of what I can take with my e part and then what else I need for my du. So the fourth thing is to actually substitute in u's. That's what substitution means. We're going to try to make this look neater and not so messy by referring back to our basic rules. This 3 I don't seem to need. If you think about it, u is x cubed. That's right up here. Du is 3x squared dx. Okay, there's the u. This piece is du. So I really am just going to substitute. I have this extra 3 constant multiplier. That was one of our rules for antiderivatives. We had a constant multiplier times a function. This 3 comes in front. This is now e to the u. All of that is du, and I've done substitution. Well, I have this rule. Before, it was e to the x. If I have the function e to the x, then the derivative is, and the antiderivative are both e to the x. This rule, if I have e to the u, is e to the u plus c. And then I can do this and go back. This is actually my step 5, and find the antiderivative. And then my last step 6 is to plug back in the original variable. 3e to the u, where's my u? Way up here, x cubed, that's u, plus c. And if we go all the way back up to where we started on the previous problem, I had 3 to the x cubed. Now, I didn't have a c, and the problem we started with, c was equal to 0, so that we just had 3e to the x cubed. There are all the 6 steps are all written out in the lesson, so you can keep track of what it is you're doing each time you do one of these problems. But this is the basic way that we do it. In this example of substitution, we have an inside of our radical, so that may be what we want to choose for you, because this is clearly more complicated than the basic 5 formulas that we have. So let's first rewrite this radical, because remember, we don't have a derivative rule for a radical either, but we do have a power rule for an integral. So let's rewrite this as the integral of 3x squared times x to the 3rd plus 1 to the 1/2 power. Remember, a radical is a 1/2 power. And so we can look here and see that there is an inside the parenthesis. And also, this power of the x cubed is bigger than the x squared. And we saw before with an x cubed example, when you take the derivative, you get x squared. And so that leads us to think this would be the inside function. So that's u. So let's let u equal x to the 3rd plus 1. And then to get du, I take the derivative of x to the 3rd. I get 3x squared. And then remember, multiply by dx. Let's see exactly what we have here. When I look back at the integral, If I want to rearrange them so they fit in the order with the u and then the du at the end, I'll have the integral of x cubed plus 1 to the 1/2 and then 3x squared dx. And that pretty much shows me what I have. I've got du right there. My u is the inside function. U is inside here. So the next step would be to actually go ahead and substitute in u and du. The integral of u to the 1/2, and all of that is du. It's just a substitution. I'm getting this integral to a form where I know the rule, the power rule. So then I can find the antiderivative. I add 1 to the exponent. Remember, that's 1 over 1 plus 1/2. U to the, and that's 3/2. I'll just keep it like that for now, and then plus c. So I have 1 over 3/2 gives me 2/3. U to the 3/2 plus c. And my last step is to go back to the variable I started with. U is equal to x to the 3rd plus 1. That's my u. And it's now to the 3/2 power plus c. So we go step by step. When I choose u, sometimes that's the most difficult. We look for something inside. If we have a couple of different powers, we look for the piece that has a bigger power. Choose u and du, and then just pick it out of the integral. Rewrite until you can see exactly what you have. Let's look at a different example. We have worked with an e to a power before, and in that problem, we had e to the u. So let's see what happens if I choose my u to be 2x. The du would be 2 dx. I do have a 2, but look what would happen. I would have 2 e to the u over 3 plus e to the u. Well, let's see now. This 2 would have to come over here and be part of the du. That's not simple. So that's not what we want to pick for u. This u, sadly, is not complicated enough. That happens when you have two things like that. Since the bottom is bigger, but includes the e to the 2x, that's what we want for our u. So we want the whole denominator to be u. And then for the derivative of 3 is 0. The derivative of e to the 2x, the derivative of e to the power is the same, and multiply by the derivative of the exponent. So that's our du. And I could rewrite this if I want to, but I think I'll just go directly over here and see what I can figure out I have here. My integral, well, actually, I really don't have to rewrite. When I look at it, all of this is du, and it's right there. That's du. And then the denominator's u. So I think I can go directly to, let's plug in the u's to substitute. The numerator and the dx over here, you can either put the du on top if you want to. The denominator is just u. Or I could write it as 1 over u du, and then it looks more like the rule that we had, the integral of 1 over x dx. When you take the antiderivative of 1 over u, you get ln natural log of u plus c. And then we go back to our original variable. ln absolute value of u was 3 plus e to the 2x plus c. So a very messy integral, if you make the correct choice for u, really can come out to be a nice, neat answer once you simplify. In this question, we're given a formula for u. U is equal to 3x squared plus 7. And our question says, which integral can be solved by this u substitution? So we're going to look at 3 integrals and see which one or more work and why the others don't. First, let's look at this one. The integral of 6x over e to the 3x squared plus 7 minus 5 dx. We're already told what u is. So u is 3x squared plus 7. And always when you know u, the next step is to find du. That's always what you do once you pick your u. The derivative here is 2 3s are 6x. Derivative of 7 is 0. So we just have 6x dx. So now let's go back to the integral and see how things fit. See what we can, if we need to rewrite or what we have here. Let's see. 6x dx, we can substitute du, and that is the whole numerator. So we can put that in. Our u, 3x squared plus 7, would go here. But it looks like there's some extra down here. If I try to write this as an integral, I'll put the 1 up there and put my du off to the side. And then this would be e to the u minus 5. Well, that is not one of the simpler rules. The whole point of u substitution is to choose a u, find the du that comes with it, and then when we put it back over here, our whole problem reduces to one of our simplest formulas. This does not. So this, because of our minus 5, and the u, e to the u is in the denominator, we can't solve this integral using u substitution. So let's try the next integral. The integral of 6x squared times the square root of 3x squared plus 7 dx. Okay, here's a radical. I know that I can rewrite that to a power. The integral of 6x squared times 3x squared plus 7 to the 1/2 dx. And I was told my u is 3x squared plus 7, so I'll use that, and it's right in here. So that part looks okay. I do have the u to a power. But my next step to get du, my du was 6x dx, but there's a little bit of an issue here. I don't just have 6x squared, 6x dx. I have an extra x. Now, if I had an extra constant, we have a formula for constant multipliers that say pull the constant in front and continue working. Well, you can't move a variable. The variable part has to stay to the right of the integral sign, to the left of the dx. So I cannot move out the x. So this u substitution does not work because we have an extra x. Okay. Well, let's try the last integral. See if there's another problem with that, or maybe we'll get one that works. The integral of 6x times 3x squared plus 7 to the 11th. Aha. Okay. We have u equals 3x squared plus 7. It is the inside function. Du is 6x dx. It's on the outside. I could rewrite this so it is in the basic order of the u part and then the du, where I write this with the u in it first, and then all of this together is du. So I do have an integral that's u to the 11th du, and that is our basic power rule formula. So I can solve this. I don't need to. Once I get here, I know I just use the power rule and I can continue. So this integral does work. I had to test u, but I had to also test du. Du was one of the keys to look for when you do these problems. In this segment, we're going to look at substitution using the power rule. We've looked at general cases of substitution before, but starting with this lesson, each lesson in the text picks one of the integration rules and has every single example focusing on that rule. Here we're going to look at the power rule. The integral of u to the nth power, du, is equal to u to the n plus 1 over n plus 1 plus c, as long as n is not equal to negative 1. The original basic formulas that we looked at just had an x in place of the u. So when you see a u in a formula, you might think about u substitution, that it indicates that this is the one we think of when we would do a more complicated function. So let's look at the integral of 3t over 4 minus 2t squared to the 5th power dt. This is definitely not just x to the n, but we do have a power down here. Note that there is a 5th power. And when you're working with a complicated function, you need to choose something to substitute so we can simplify. So u is going to be what's inside our parenthesis that is raised to a power, because we notice u to the n, u is the whole thing in the parenthesis. So let's choose u as 4 minus 2t squared. Not the exponent, just what's inside. And to get the du, we'll take the derivative. Derivative of 4 is 0, minus 2t squared. The derivative would be 2 times 2 is 4, t to the first. And to get the du part of the derivative, we multiply this by dt. So first step is to get u, second step is to take its derivative. Third step is to go back now and try to arrange the integral to fit what we've got over here. I don't see a 3 over here anywhere, so I'm going to move the 3 in front, which leaves me with the t, and I have the dt, and I have the denominator 4 minus 2t squared to the 5th. Now, it doesn't match exactly because this is a t dt, but over here I have negative 4t dt. But I can put in a constant as long as I remember to take it out. Remember that you can always multiply by negative 1, and negative 4 over negative 4 is 1. You can't multiply by negative 1, you multiply by 1. And that's what I have here, a negative 4 on top and a negative 4 on the bottom. So I have not changed the value of the integral at all. And from this step, I can say, okay, keep the 3 over negative 4, or I'll make it negative 3 over 4. All of this top is the du. I'm going to put a 1 there and put my du off to the side. And under here is u to the 5th. Well, that doesn't actually fit the power rule because this is in the denominator, and the power rule says it just has to be no denominator. But that's when we bring that up and make it a negative exponent. So I'm still at my negative 3/4. Now I have u to the negative 5th du, and now I can do the antiderivative. So negative 3/4 is the constant. For u to the negative 5th, you add 1, makes it u to the negative 4 over negative 4 plus c. And I'll simplify that a little bit. Let's put the constants together. A negative 3, 4 times negative 4 is negative 16. That gives me 3/16. My u to the negative 4 would be 1 over u to the 4th plus c. And then the last step is to take whatever u was equal to and put it back in here. So my final answer would be 3/16 times 1 over u, which is 4 minus 2t squared, now to the 4th power plus c. And there are various ways to write this. You might see this written with the 3 on top and the 16 on the bottom with the rest of the function. But this in general is what you will see when you have your antiderivative with u substitution using the power rule. Let's look at this example now. The integral of 1 over y times the quantity ln of y squared to the 3rd power dy. So y is our variable, and we have to look again, what rule do we use? This is in the section called power rule, so we look for a power. So what's inside here must be the base u for the power rule. So u is natural log of y squared. And we have to take the derivative. To get du, we take the derivative. The rule for natural log of a number, ln of u, is 1 over u, so it's 1 over y squared, and then multiply by the derivative of that u, which would be 2y. And then the dy to make this the du instead of the derivative. Now that 2y and the y squared, we can cancel y's. So du is actually 2 on top, y on the bottom times dy. Let's go back now and see if we can arrange this to fit what we know with u and du. This ln of y squared in a parenthesis cubed, I have this y in the bottom really looks like it goes with the du. So I'm going to move it and keep the 1 over ln of y squared to the third, and then this is times 1 over y dy. So if you look at this, it's a funny looking d. This is the same as this. I just split up my fraction. 1 times 1, and then the denominators multiply. But when I do this, I see that the y in the bottom and the dy are here, but I'm missing a 2. So let me do this one in color. Let's put in a 2. And then that would put a 1/2 in front, because 1/2 times 2 is 1, and constants can move in and out, but you can only put in a 1, which would be 2 over 2. Writing this now in terms of u and du, it's 1/2 the integral 1 over u to the third. And all of this right here, we substitute this whole thing equals du. And it's similar to what we just had in the previous problem. 1/2 the integral of u to the -3 du. We do the power rule. I have 1/2. When I add 1, it's u to the -2 over -2, and then plus c. And we'll put it back together like we had. Always try to get it similar to what you start with usually, and we pretty much never leave a negative exponent in an answer. We've got 2 times -2 in the denominator. We'll call that -1/4. The u to the -2 becomes 1 over u squared plus c. So this one, I think I'll write this all together. -1 over 4 times u squared. U is ln of y squared. It is squared, and then plus c. Now you can, if you feel like everything is so messy and you want to take the derivative to see if you did it right, sometimes the derivatives are so much messier, you ought to just go back and check your work. Or if you're not sure, ask for help. Or look for the answer if it comes from the lessons. You can always look at those solutions. In this segment, we'll look at substitution again, this time with the 1 over u rule, the rule that gives us a logarithm in our answer, logarithm of the function. Remember, it's the same basically as the integral of 1 over x dx equals ln absolute value of x plus c. We'll just have more complicated functions that don't always make this look very evident. So let's look at the integral of 2 over 5x plus 2 dx. This actually looks pretty simple compared to some of the ones we've even already looked at. The x is in the denominator, but if you have an x in the denominator and you want to work with it, you choose the whole denominator for your u. It's the most complicated part of this fraction. So that u would equal 5x plus 2. Next, you'll take the derivative of it. The derivative of 5x is 5. Derivative of 2 is 0. So it would be dx in order to get the du. The derivative would be du dx equal to 5. We multiply the dx across. So from here, we want to see what we've got for u and du and how we can fit those back in here. Well, one thing we don't have is a 2 by itself. So this 2 is a constant multiplier that moves in front. and that leaves us a 1 on top over the 5x plus 2 dx. But I need a 5 to go with my dx, so I'll have to just put it in. So I'll put in the 5, put it right up here, and put the 1/5 in front, or put the 5 in the denominator, however you want to think about it. I just put in and take out what I need. And I now have exactly what I need. All of this piece right here will be the du. And I can write 2/5 times the integral of 1 over u. And then all of that comes over there to be du. So I do have the rule 1 over u du. That equals 2/5 times natural log, absolute value of u, plus c. And so the final answer means just put the x's back in. 2/5 absolute, ln absolute value of 5x plus 2. When you want to substitute u back in, if you go up where you wrote it, that is the easiest way to find out what it was, instead of trying to look back in the original integral. So this would be the final answer. Now we're going to look at a slightly more complicated version of a 1 over u problem. When you first look at this, though, if you see 2 to the 5t, you may think u is the exponent 5t. But if you do that, you're going to end up with a 2 to the u here, 4 plus 2 to the u there. It really makes it more complicated, so that's not what we're going to do. Whenever you have 2 of the same thing, you want to pick one with a bigger piece to be your u. So we'll take the whole denominator to equal u. So u is equal to 4 plus 2 to the 5t power, and we need the derivative. To get du, derivative of 4 is 0, plus the derivative of 2 to the 5t, 2 to the u. Okay, that's the derivative formula that gives us ln of 2 to begin with, natural log of the base, times the function that you started with, 2 to the 5t, but then the 5t, we talked about it being 2 to the u because this is not just 2 to the t. We have to multiply by the derivative of 5t, which is 5. And then we get the dt on there to give us the du part. So all of this, and then the chain rule, the derivative that gives us 5, all of that is du. We don't have a lot of that in this problem, so we need to really put some things in. So let's see what we do have. What we have already as far as du is 2 to the 5t here and the dt. Now ln of 2 is a constant, 5 is a constant, so we just put them in. If I put in the 5, it goes on top with this exponential part. I have to put it underneath in front. I left a space because I need this ln of 2, so I have to put that in and put it in the denominator. So we have a big fraction in front and then all of this inside. So let's now try to match this up with u's and the du. The part in front stays constant, so that won't move. ln of 2 times 5. My integral, all of this on top is du, every bit of it. So I just substitute. All of that goes up there. You can either put it on top or out on the side where the dt is. And then in the bottom, I have u. So it just substitutes in there exactly. Now you can write it like this, or if you prefer, you can put the 1 back up there and then just put the du out to the side like you have the dt. Doesn't make any difference. So I have a fraction in front, 1 over ln of 2 times 5, and then the antiderivative of 1 over u is natural log absolute value of u plus c. And I'll just put my u back in and we'll be done. 1 over natural log of 2 times 5 multiplied by the natural log of 4 plus 2 raised to the 5t power plus c. And with this one, 4 is a constant. I'm adding 2 to the 5t. All of this that's inside here is positive. So even though I wrote it because the rule says it's absolute value, it would be appropriate here, because no matter what I put in for t, I don't get a negative, to write this instead of with absolute values. I could just write it with parentheses. That would also be correct. This segment we're going to look at substitution with both exponential function rules. In the lesson, you get a lot of examples on both of these rules in that same lesson. We'll just do an example of the exponential function that's the natural exponential, base e, the integral of e to the u du equals e to the u plus c. And then we'll do an example with the general exponential function, the integral of a to the u du equals 1 over ln a times a to the u plus c. So let's first look at one that has an e as the base. The integral of 3x e to the 4x squared dx. Whenever there's an e, you look to the exponent because we have a rule for e to the u. So in here, our first guess would be that u is 4x squared. To find du, we take the derivative, would give us 8x, and then dx. So when we look back at the integral now, we have e to the u. That's how we got our u. But the du is not all present here. We have a 3 and we don't have the 8. So we move the 3 in front of the integral times x e to the 4x squared dx. And since we need an 8 and we don't have it, we put it in. We have the x and the dx, but not the 8. So let's write in the 8 and divide by it in the front. Multiply by 8, divide by 8 gives us 1. So we have not changed the value of the integral. And then the next step would be to put the u and the du in. 3 over 8 times the integral. And I have 8x dx. All of this together is du. E to the 4x squared is e to the u. And the antiderivative of e to the u is e to the u. So this is 3/8 e to the u plus c. Put the original variable back in, is 3/8 e to the, what was u? 4x squared plus c. So if you have an e to the u, your answer for the antiderivative is not exactly the same as what you have inside your integral. The derivative of e to the x is the same as the antiderivative of e to the x, is the same as the function. But if it's e to the u, you will get differences. So that's why substitution for a case like this is so very important. Now let's look at this example of a to the u. When you look in here, you see an exponent. And so since the base is the constant, it's the a to the u formula. So just looking at that piece right there tells you what you need to look at for u. This is the part that is the power of the base, and so that would fit the formula for a to the u. So that u would equal t squared plus 4t, and then du would be 2t plus 4 dt. Now, when you look back in the integral, we don't have a 2t plus 4, but we do have a t plus 2. So if I factor out a 2 here, I can match up what I have in the integral with what I have for du. I have t plus 2 dt, and over here I have t plus 2 dt. What I don't have is a 2. So let's come down and put in what I'm missing. I'm going to keep my 4.5 to the t squared plus 4t. My ln of 4.5, when I go to look at that, it's not here at all as part of u or du. So let's put that to the left. That's a constant. That doesn't look like it's needed in the u and the du. 4.5 to the t squared plus 4t, ln of 4.5. Over here, I can now do my t plus 2 dt. Let's see, I'm missing the 2, but I have every other piece now, there and there and there, that I need in the integral, but I don't have this 2 right here. So let's put that in and take it out. Okay. So I have this pretty much written in the order that I need to use it. I have this constant natural log of 4.5 over 2, this part, the integral sign, and then the a to the u, a is 4.5. And then all of this 2t plus 2 times dt is du. So using the u substitution here, it really did shrink whatever is inside the integral. I still have that constant in the front. So I keep the constant, ln of 4.5 over 2. And when I take the antiderivative, the rule says 1 over natural log of the base. So I multiply this by 1 over ln of 4.5 times 4.5 to the u, and then plus c. Well, you'll notice here, see, all of this is the antiderivative part. But I have an ln of 4.5 on the bottom and one on top. They'll cancel. So I have 1/2 in front now, 4.5 to the u, plus c, and I put my original variable back in. 1/2, 4.5 to the, here's u right up here, t squared plus 4t plus c. That's quite a complicated problem, so be sure to take a good look at this. And be sure that you understand step by step what you get. The steps are the same as the ones we've been doing. Okay. In this segment, we're going to look at integrals that require simplification, and some may need also use substitution and some may not. For this one, let's just look at this integral, y squared plus 3, that quantity to b squared dy. Now when we look at this, we think use substitution because there's a power and we have a power rule. So let's try to let u equal what's inside. So if u is y squared plus 3, du would be the derivative of y squared is 2y, derivative of 3 is 0, so we have 2y dy. Well, the 2 is not an issue. I don't have a 2 outside here, but I could put that in. But I don't have that y. This y is missing. You cannot put in a variable. So that means use substitution does not work. But in order to simplify, I can multiply it out. So we multiply y squared plus 3 times y squared plus 3. That's how you square. And that would give us y to the 4th plus 6y squared plus 9 dy. And now what we have to work with is sum and difference rule. So we had to simplify to do this one, but there was no use substitution involved because our next step is to use individual rules, sums, no differences. The antiderivative of y to the 4th would be y to the 5th over 5. Plus 6 is a constant multiplier. Antiderivative of y to the y squared is y to the 3rd over 3. Plus 9 is a constant, so I multiply it by the variable of integration, which is y, and then plus c. So I could simplify and make this 2y cubed, but this would be what we have. We simplify by having to multiply it out. We could not use use substitution on it. And then we took each piece individually. Here's one that's more complicated. We have an e to the x, so you might think about use substitution with e to a power, but it's just x. You might think about trying to do a use substitution on the whole numerator. Most of the problems you will see, you can choose u to be the whole denominator, but you seldom have u being the numerator. So let's see if we can simplify, and because we have two terms in the numerator and one in the denominator, we can split up the fractions. So I can write this as the integral of x squared e to the x over x squared minus 3x over x squared dx. And I have two separate fractions. And I can simplify the fractions further. Integral of e to the x minus 3 over x. And both of these are in terms of an x. I can rewrite it a little bit more to make it easier to look at. Maybe this would be 3 times 1 over x. And then I can do antiderivative of each one separately. So I would have antiderivative of e to the x is e to the x minus my multiplier 3, and the antiderivative of 1 over x is natural log absolute value of x plus c. So this one I had to do simplification on, simplify, but there was no u substitution. It looked like it might be. It was kind of complicated to begin with, but rewriting in two separate fractions and working made that work out very neatly. Now this problem has natural log in it and an e in it, and a t squared in the bottom, all kinds of stuff there. But again, it's one of those fractions, and we can rewrite it by splitting it up into two parts. So let's do that and write t ln of t over t squared plus t to the third e to the t squared over t squared dt. So I have two separate fractions. And this time when I simplify and I cancel, this t goes away. I'm left with ln of t over t. And I think I'm going to go ahead and do two separate integrals. So I'll put a dt with that one and then plus the integral. When I simplify this, I get t e to the t squared dt. So I've done my simplifying. But I don't have simple things left. In this case, I do need u substitution. So to here, let's simplify. So that part's done. But the next thing I do have to do is u substitution. And it looks like I'm going to have to do two u substitutions, one for each integral. So let's just look at this piece first. Here I have ln of t over t. Let's let u equal the worst part, which is the ln of t. Then du, derivative of natural log of t, is 1 over t dt. So this integral could be written as ln of t times 1 over t, and then dt. This t can slide over there, which makes it u du. So I'm working all the way down this integral before I do the other one. This would be u squared over 2 plus c, and then that would give me, I'm going to move the 2 in front to 1/2, natural log, here we go, right here, natural log of t squared plus, I think I'll make that c1. Because now I have to come over here and go plus, and let's do the other piece. Okay, so this side I've completed. I'm going to add that result to whatever I get here. Here I have e to a power, so let's let the power be u. U is t squared. Then my du would be 2t dt, take the derivative. I have the t dt, I have that part, I don't have the 2. So in that integral, I need to put in a 2 and put a 1/2 in front. And this is one of the reasons why it's very important to separate. We don't want to put the 1/2 in front of everything. It only refers to this piece. So I have 1/2, the integral, and my 2t and my dt are the du. And what's left here is e to the u. So the antiderivative of that would be 1/2 e to the u plus c, or 1/2 e to the t squared plus c, and let's call this c2. And now I can put these together. I want to add. So my final answer is 1/2 natural log of t squared plus 1/2 e to the t squared plus c, where I add both the c1 and the c2 together to get c. Our last example in the section on integrals that require simplification already looks about as simple as it can get. The antiderivative of ln x dx. It can't be simplified. You cannot use substitution. In this course, you cannot solve this integral. It can be done by other methods that we don't use, and so this cannot be done by simplification. It cannot be done by substitution. You can't do it in this course at all. It does not equal 1 over x. Remember, the integral of 1 over x dx equals natural log of x plus c. It's not the integral of ln x. So this is the way we work with it. We cannot do that, okay? Not done in this course. And it certainly cannot be done by a simplification or use substitution. We're going to look now at substitution with business applications. Now, sometimes when we do business applications with these antiderivatives, we use the marginals, marginal cost, marginal profit, marginal revenue. Other marginals are out there also. But they're not all marginal. Sometimes they can just be a rate of change of something that does also relate to business. So that's what you'll find in this section. So we'll look at an example now that's just a rate of increase. Okay, so the problem says that the rate of increase in the total number of books sold online. Now, that's a rate of increase in the total number of books sold online. And since it's a rate of increase, this is a per year rate. And it's actually in millions of books per year. So our formula is B of t equal to 83 e to the 1.97t power over 22 plus e to the 1.97t power. This is the rate of increase in the total number of books sold online in millions of books per year. And this is between 1997 and 2000. So that our t equal to 0 is the year 1997. Now, what we want to find is the total number of books sold, beginning in 1997, going to wherever we intend to go. So we're looking for a formula that will just let us plug in a year, based on year 0 being 1997. Well, if this is the rate of increase in the total number of books, then what we want is the antiderivative of this rate. So to find the total number of books based on this rate of increase, my number of books, n of t, would be the antiderivative of b of t dt. So I can take the antiderivative of our formula, dt, and know that that's based on time t starting in 1997. And in order to do this, it looks definitely like we need to use substitution. Since I have two e's, I'll let the whole denominator be u. And so to get du, derivative of 22 is 0, plus the derivative of the exponential part would be e to the 1.97t. Because of the chain rule, we multiply by the derivative of the exponent, which is 1.97. and then put the dt on the end. So when we look back over here, looks like I do have some jiggling to do because I don't have a 1.97 and I do have an 83. So let's rewrite this. Move the 83 in front. E to the 1.97t over 22 plus e to the 1.97t. And I have to put in my 1.97 and I have to take out 1.97. So it's pretty clear. All of this on top is du, and in the denominator is u. So this equals 83 over 1.97 times the integral of 1 over u du. All of this we can write as 1, and everything else goes into du. So 83 over 1.97, antiderivative of 1 over u is ln of u plus c. So we have 83 over 1.97 natural log of all of this, 22 plus e to the 1.97t plus c. Now, since this is a real formula for a business, we need to figure out what c is equal to. So we started t equal to 0 was year 1997. And when we start, we had nothing as far as this is where we started counting, so there were no books previous to that. We just started counting. So we can say that n at time 0 was 0. So we do have an initial condition we can use. So we take our formula, let's go back up, give us some room, and solve for c. Maybe I'll work up. This is n of t. If I want n of 0, I'll put 0 in for t. This number, if you multiply it all out, is 42.132. Natural log of 22 plus e to the 1.97 times 0 is e to the 0 plus c. And all that actually equals 0. Oops, better leave that. So this is 0 equal to all of this, 42.132 natural log of 23 plus c. When I multiply out and solve for c, move this to the other side of the equation, I found out that c is equal to a negative 132.10. So that I let t equal 0. When I set that equal to 0 and solve for c, this is what I get for c. So my actual formula for n of t is this expression minus 132.10. So our final answer, n of t, would be 42.132 natural log of 22 plus e to the 1.97t minus 132.10. That would give us the actual number of books where t is some year number since 1997. The year 2000, for instance, t would equal 3. You'd plug that in, get your number, and that would give you the number of books sold online since that time. So in our application, we're talking about the marginal price of bottles of baby shampoo. The weekly demand is 150 bottles when the price is $4. The marginal price gives us an estimate of one additional item, but we want the whole demand equation. We want to find, given the marginal price equation, find the price demand equation. So our P of Q, our actual demand equation, would be the antiderivative of P prime dQ. So it's the antiderivative of this function, negative 6,000 over 3q plus 50 squared dq. dq tells us our variable is q. Now, it definitely looks like a U substitution problem. We have something raised to the second power. So we'll let u equal 3q plus 50. du then would be 3 dq. And when we look back over here, we don't actually have a 3. We do have a negative 6,000. So let's rearrange this a little bit. Let's pull the negative 6,000 in front. I'll have a 1 left, dq, over 3q plus 50 squared. And I can put a 3 in where I need it here, and then divide by 3. So I have negative 2,000 times the integral. All of this is du. And under here, I have u squared. So we have to rewrite that as negative 2,000, the integral of u to the negative 2 du. And when we take the antiderivative of that, we have our negative 2,000. And this will give us u to the negative 1 over negative 1 plus c. So we need to work with this and our initial condition here to try to solve our problem. So P of 150 is 4. That means my price is 4. Over here, this is negative 2,000, but that's negative 1, makes this plus 2,000. Over u. This is negative 1 divided by u. That's what our u to the negative 1 gives us. U was erased, 3q plus 50, and then we have a plus c. Our q now has to be 150 when I have 4. Let me call that p of q. And then when q is 150, this is 4. 2,000 over 3 times 150 plus 50 plus c. 450 plus 50 is 500. 2,000 divided by 500 is 4. So I have 4 equal to 4 plus c gives me c equal to 0. So the function that I have to work with, my final function, is 2,000 over 3q plus 50. So it turns out to be a much smaller function than you would think when you start off and go through all your substitutions. It took a little bit more than usual to solve for c, and then we found out it was 0. So the antiderivative of this is 2,000 over 3q plus 50. That is our demand equation. If you have a quantity you want to find out 200, you'd plug in 200 here, do the multiplication, addition, division, and that would tell you how much you need to charge when you're selling 200 of your bottles of shampoo instead of 150.